Okay, let's continue this discussion for chapter 19. I'm going to define something in here called entropy. Let me see how I'm going to define it, okay? First of all, note the following. QC, if you guys remember, I'm going to take it in numerical value. I calculated it. Let me use the black pen, okay? I don't really like the red pen anyway. Change the colors. But let me tell you what I found QC from the previous calculations. Remember, QC was equal to minus nRTC ln of VC over VD, and QH is equal to nRTH ln of VB over VA. Okay, these two ln's are the same thing. Okay, as a matter of fact, I'm going to call VB over VA compression rate. Okay, VB over VA is compression rate. Okay, so by definition, CR is equal to VB over VA, and it's the same thing if I use the log expression. That ratio is the same basically if this is raised to, in other words, and so is VD over VC. It's the same CR. Okay, so this is also VD over VC. Okay, so that's the compression rate. Okay, did I say VD? I'm sorry, it's VC over VD. Control Z. Doesn't make sense. It's the big volume over the small volume always. So this is VC over VD. So this volume to this volume is the ratio of this volume to this volume. So that's basically what the compression rate in this case is. I'm going to write it in terms of CR now. So QC is equal to minus nRTC ln of CR, compression rate, ratio of the two volumes, the big one over the small one, and it's the same too. Okay, and QH is equal to positive nRTH, the same log of CR. Okay, if I do the following, if I take the first expression and divide it by TC, this gives me QC over TC is equal to minus NR ln of CR. This is a number, okay? Doesn't matter what that is. There's so many joules per Kelvin. And this one is QH divided by TH. It's the same thing, actually. It's a positive NR ln of the same number. So they are two the same thing. So if I add them both side by side, I get 0. So if I add this side to that side, on this side I have 0 because it's the same number. One of them is negative, the other one is positive. So what I end up with is QC over TC plus QH over TH is a quantity that doesn't change in the entire cycle, for at least Carnot cycle. Okay. In other words, if I go from point A and tally the amount of heat over the temperature through the entire process. Remember, there is no heat in the adiabatic process. That's why I didn't care to add this two. If you want to add 0 to both processes, add 0 during this expansion and subtract 0 during this expansion. I'm sorry, subtract 0 in here and add 0 in there. It doesn't matter. You're going to end up with 0 added to these two expressions. So what I'm saying in here is that this quantity is conserved toward the entire cycle. Heat is not a conserved quantity for a cycle. Work is not a conserved quantity for a cycle. Energy is, though. Okay, the pressure is too, because they start from the same pressure, come back to the same pressure, so the difference in pressure is the same, 0. The temperature is also a conserved quantity. If I start from this point and come back to it somehow, I will always end up in the same temperature. So there is no change in temperature if I go through a cycle. There is no change in volume if I come back to the same cycle. There is no change in energy if I come back to the same cycle. This too seems to be a quantity that doesn't change with volume. I mean, that doesn't change with the cycle. So in other words, the quantity, if I sum it up, dq over t, this quantity over a cycle is 0. Okay? This quantity over a cycle is 0 for the entire process in this case. Okay? provided that this integral is closed integral through a path in here. So I'm going to call this quantity the entropy. So the quantity entropy ds is by definition dq over t. So this is the entropy. Okay, so this is another quantity that is also seems to be a state variable, meaning that if you go from point to point to point to point to point to point and come back to the same starting point, it should be 0 through this process in here, at least in here. Okay, the process is reversible, that's why the quantity is 0 in this case. Okay, the second law actually can be formulated in a different way using the entropy actually. So this is the modern interpretation of the modern basically statement of the second law, is that the entropy always during any natural process increase or at best equal to 0. That is equivalent. I'm not going to prove that in here, but if you do statistical mechanics, the proof for it is a little bit straightforward, that the entropy is equal at best is equal to 0 in a reversible process like this one, and in a more general process that is not irreversible, accompanied with the heat exchange, heat loss, and other mechanism, then in this case the entropy will always increase. So the entropy of the universe will always increase. Okay, so this is equivalent to the second law of thermodynamics. So now you have two statements of the second law of thermodynamics. So part of the questions of the day today is this one too, that you're supposed to restate the second law of thermodynamics in two ways. Okay, so the first way is the way that we did it in the previous part, and the second way is in terms of the entropy. So the entropy always increases in a natural process. At best is going to be equal to 0 in a reversible process. So that's basically what it is. Another way of actually expressing, if you use statistical mechanics, the entropy is related to something else, which is the number of microstates. Basically, if I take a gas, that's also another thing in here, that is isolated on one side, or if I take, for example, a cup of water, for example, and add to it a little bit of different coloring food, for example, of substance, we will see that because of the entropy increasing in the system, that the coloring will spread throughout. The same thing that caused actually the coffee from getting from hot coffee to cooling down, it's the same thing in here in this case. Obviously, when the temperature of the hot coffee will went down, actually its entropy went down, actually did not go up. But if you consider the environment around it, actually the entropy of that environment went up, and the net effect in this case is the entropy of the universe actually will go up. Okay, so again, if I take in here a cylinder in here and have a gas on one side, and if I move this cylinder up so that there will be an opening in here for the gas to escape, I notice that the gas will fill the rest of the volume in this case. So the entropy is actually related to how many ways I can move, or how many ways the energy actually is distributed in a gas, because if it expands there are more ways for it, and this is something in statistical mechanics referred to as the number of microstates. Mr. Boltzmann showed, and we're not going to go through the derivation in here, that the entropy is related to the number of the so-called microstates. I think the book uses the lowercase w, okay, but usually is actually written as omega, capital omega. Okay, so this is the famous Boltzmann entropy expression. When people visit Vienna, this is one of the things they go and see, that is basically engraved on, written on his grave. People go there and basically remember the great man he was, because he did so many things for us in science. like I mentioned before, he committed suicide at the end. So we're not going to get into a lot of details. I think there are some exercises related to the entropy, to calculating the microstates, which is if you took a branch of mathematics, the permutations. That is basically in how many ways you can arrange different microstates to get a macrostate, to get the observable thing, which is at the big level. That is how you do that in statistical mechanics. Okay. Please read the chapter. At least there is a small section on statistical mechanics in this chapter, but the emphasis is actually on the way that we defined it above and here on how to calculate the entropy in this case. Okay. Now, let's see here where we stand in terms of the entire chapter. We're going to do more examples of obviously with this thing in here. So we found the efficiency, we found all kinds of things in here for a Carnot cycle. That's how we did it. We didn't do it for everything, so that you guys are, if you're not following in here. So let's calculate the entropy in here and show it at least for a simple case in here. For a case where I have water sitting at, let's say for example, 20 grams of water sitting at 20 degrees Celsius, room temperature, okay? And then I have another quantity of water. I just want to stick with water in here because I know what the specific heats are. If you have something else, you can always involve the specific heats for those ones. And if you have, for example, a different phase, for example, a solid ice, for example, you have to include the latent heat in that to calculate the entropy. Okay, but then just the integral is just the integral of 1 over t in that case, which is negative 1 over t squared. Remember, dq in the during a phase transition is L, okay, times the mass in this case. So in this case I have 20 grams, so if I have it in, so if I define in this case ds simply will become ml over t, and times, of course, I'm sorry, which is just a constant, so the integration over the temperature in this case will be just, it's going to happen as the same constant. So that's how much the entire delta S in this case. So I'm sorry, I mentioned something earlier. So the change in entropy is just the amount of heat in this case divided by the temperature, because the entire phase transition happens at the same temperature. So that's how much it is during a phase transition. But during a same phase, for example, going, let's take for example 10 grams of water sitting at 80 degrees Celsius, then we have a problem in this case. We really have to integrate in here to find the entire entropy. So obviously, first of all, I need to find the temperature of equilibrium. So the hot water, which is sitting at 80 degrees Celsius, its temperature will go down and to a temperature where both of them will be in equilibrium, times, of course, the 10 grams times the specific heat, which is 1 calorie per gram per degree Celsius. So this will be the amount of heat taken by the cold one, which is 20 grams times 1, it's the same substance, times the T equilibrium, where we reach that, minus 20 degrees Celsius. I'm going to solve this equation for T equilibrium because we need to find where the mixture will go, and then we're going to calculate the temperature. So we have 20 grams sitting at 20 degrees Celsius, and we mix it with an 10 grams, I'm sorry, sitting at an 80 degrees Celsius, and the temperature of equilibrium is somewhere in between. It's not necessarily going to be exactly the middle because we have different quantities of this. Okay, so it's going to be 10. Of course, the 10 cancels the 0 cancels the 0, and we will have in here 80 minus T equilibrium is equal to 2 times T equilibrium minus 40. 40 minus 80, no, 40 when I take it to the OSR, it's going to be 120 actually, is equal to 3 TeQ, and if I divide that by 3, I'm going to get the temperature of equilibrium being 40 degrees Celsius. Okay, so that is where they come up to. So the 20 grams will go up by 20 degrees, and the 10 grams will come by 60 degrees. By, is it 60? I'm sorry, 40 degrees, so that they meet in the middle somewhere around 20 degrees. So that is basically something that we learned from calorimetry, and I'm sure you did a lot of this in chemistry. That's not really the point in here. I want to find the entropy in here. So I want to find the entropy of this this water. So what I'm going to say in here, ds is equal to dq over dt when the water goes by dt temperature. dq is actually going to be mc times dt over t. Now if I'm going to integrate from t initial to t final, of course I have to consider both the cold source and the hot source and see where the entropy of both systems is going to end up in. So delta S in general, the change in the entropy, is going to be mc, which is constant, the mass times the specific heat, from t initial to t final of dt over t, and we have seen this integral several times in thermodynamics, which is just the ln of t final over t initial. Obviously, if t final is higher than t initial, then there is an increase in temperature. So the water whose temperature went up from 20 degrees to 40 degrees, it sees an increase in the entropy. However, the water that has its T final less than its T initial, it will see a decrease in the entropy. What is more important about the second law in here is that it states that the universe entropy will increase. So what I expect to see is that this one, the positive one, so I have two types of increases in here. So this went up, so the entropy went up. This went down, so the entropy went down. And I expect this number to be algebraically higher than this one, so that at the end I will have a positive increase for the when I add them up, because this is a process that the universe was undisturbed until I took a hot cup of water, that is only 10 grams, and a cold cup of water and put them in contact with one another. One of them, the entropy went up, and the other one went down. But what I'm saying in here is that the entropy for the entire system must go up, okay? For the entire universe, that is, before this event happened. So let me, one thing that I did not mention before, and hopefully you guys picked up on it right away, is that this T must be in Kelvin. T in Kelvin. So although the expression for dq in this case was really irrelevant in terms of writing it, because you're writing the difference in temperature, for mc the change in different temperature, but this expression, the denominator, requires the Kelvin. So this ratio here has to be in Kelvin. So again, warning in here. So let's find the cold going to 40 degrees Celsius. Remember, we have 20 grams. So I expect the number to be positive, and it should be, because the numerator in here is greater than the denominator. So delta S1 is going to be M, remember, was 20 grams, times C, which is 1 calorie per degree Celsius, per gram, times the gram is cancelled per gram. So we're dealing only with calories, and that's another thing I didn't mention about the units in here. Usually it's in joules per Kelvin, but in this case we're going to find it in actually calories per degree Celsius, which is, you have to make the correct conversion. How should I call it? Conversion, to find it in the other system. So it's going to be ln of 40 plus 273 divided by 20 plus 273, and this will be a positive number. So let me see if I can quickly find. So I have 20 times ln of 273 plus 40, so it's going to be 1.32, positive 1.32 calories per degree Celsius, okay? Or Kelvin if you like, because per degree is the same thing. Per degree Kelvin or per Kelvin or per degree Celsius, okay? But you have to do the conversion correctly in here to find it in joules. Okay, never mind the units for right now. Just focus on the positive and the negative stuff. So the hot one now went from, again, it went to 40 degrees Celsius. That's the temperature of the equilibrium. Delta S2 now is equal to 10 grams only, remember, times 1, that's the same specific heat, times the ln of the final, which is still 40 plus 273, divided by the initial, which was 80 plus 273. Obviously this number is going to be negative, So this seems to violate the second law of thermodynamics. Okay, this seems to be in violation of the law of thermodynamics. So let's fix this thing in here and see how much number it is. Okay, what I'm saying in there, that law is for the entire universe. Again, ln of the same numerator, which is 313 degrees, 313 Kelvin, I'm sorry, divided by 80 plus, so add to it 20, add to it 40 actually, 353. So it's going to be a negative number as I expected it, 1.20. So this number is negative 1.20. Again, keep the same units for the sake of arguments in here. So the entropy for the entire universe now is, there is only two of them in this case, only the first and the second. So it's going to be a positive 1.32 minus 1.20. So one of them, the entropy went up, the other one went down, but the entire universe must have gone up by an amount which is 0.12 calories per degree Celsius. That is really in compliance with the second law of thermodynamics. Okay, so this is still states that the entropy of the universe went up by actually this amount. So the fact that you put your cup of hot water in the and it's getting cooler, it doesn't, yes, its own entropy is going down, but that of the universe is actually going up. Same thing, for example, living organisms, when they go and take food, for example, their own organization system will increase, so their own entropy will go down, but that of the universe is still going up. Okay, because that food sometimes it's going to be wasted, and then of course it's involved with heat loss, and then at the end the entropy of the universe will always go up, no matter how you look at it. So this is basically in a nutshell how this calculation is done. So and it's used extensively, the entropy, in every single system. Okay, and the only way to justify a process that can happen spontaneously, if this is true. Now, if the calculations will yield that the entropy must go down, so you really need to involve some sort of an input of an energy from somewhere else to calculate to end up with an entropy that at least at best is going to be zero, which is not possible. It's going to still up. So a refrigerator, for example, take a warm object and put it in the refrigerator, it becomes colder, so its own entropy went up. But don't forget that the exhaust system from the refrigerator at the back of the refrigerator will still dump a lot of heat in the environment, so that will increase the entropy, and it's going to be more than the gain in entropy in this case, or the loss in entropy in this case for the gas, for the objects, I'm sorry, that you put in the refrigerator. So for a Carnot cycle, for example, we calculated it and we saw the entropy is zero. So that is an ideal system. That's the secret why actually the Carnot cycle is not, you cannot beat it. So let's talk about the problem 56 right now, and then I'm going to get into 4 more problems. So problem 56 in here, I'm going to look at it, and hopefully you guys will understand that part of the demo that I included actually with this video, which is the Stirling engine. So the Stirling engine is 4-stroke cycle, which is relay. So I'm going to start operating between. So this is the problem 56 on page 676 in the book. Okay. So we have a PV diagram. And what we have, I think they labeled them differently, but that's fine. So we start from point C, go down on an isothermal to point D, and then go straight down at constant volume. The volume is the same to point A. So this is part of the cycle is isochoric process, and in here actually is also an isochoric process at constant volume. So the B now is at constant volume, and this is the second isothermal. So this is your TH and this is your T cold, and these two processes are happening in the same volume, which you can call VA or VB, doesn't matter what you call it. So this is V2, this is V1, it's the same volume, V1, and the pressures are not the same though. Okay, the pressures are not the same though, because this is a decompression. I mean, it's a decompression, and this is a compression because we're increasing the pressure in this case. Okay, this is happening even at a different pressure. So this is PC, this is PD, this is PB, and this is PA. Okay, so that's how this looks like. Obviously, the efficiency of this engine is here. Okay, this is, I'm sorry, not the efficiency. This is the work of the engine that is effectively what we get out of it. Okay. Now let's see how that works. Okay, so let's answer the questions first, question by question. Show that PC, so the first question, show that PC over I'm sorry, I've I called earlier the CR, it's a different name for it. It's the volume ratio, not the pressure ratio. This one is actually the pressure ratio, I'm sorry. So you have PC over PD is the same as PB over BA. So we're supposed to show the ratio of these two pressures. Okay, the ratio of PC over PD, this ratio over this ratio, is the same as that ratio over the other ratio. Okay, so this is the characteristic of your engine in this case. It's not that of the volume. Okay, this is the characteristic is based on pressures because the volumes are the same. So let's see here how that works. Okay, I know the points C and D are on the same isothermal. So I know that PC times VC is equal to PD times VD, because all of them, they are equal to nRTH, because this is an isothermal. So the product of the pressure and the volume in here is the same as the product of the pressure in here and the volume in here, because both of them are equal to nRTH. Okay. One more thing about this expression in here is that let me do the other one too. Okay, so it's where we want to do the VC is, by the way, is equal to V1, and VD is equal to V2. So we can write it as PC V1 is equal to PD V2, because it's the same volume. Okay, from the diagram. The same thing, I'm going to look at the second isothermal. What it tells me is that let's look at it in here. PB times VB is equal to PA times VA, which is equal to nRTC. Again, this is another isothermal in here. Okay, so however, VB is the same thing as V1, and VA is the same thing as V2. I'm sorry, what is this thing in here coming out? Okay, that is because of this, the volume for D and A are the same, so that's why I subbed them for V2. I'm going to take the ratio here of PC over PD, PC over VD, PC over VD, I'm sorry, PC over PD. It's clear from this expression is V2 over V1, just from straight out this expression here. It's V2 over V1. The same thing, I'm going to take PB over PA, PB over PB over VA from this expression now. PB over PA, that ratio, is also V2 over V1. Close this nonsense in here. Why is it popping up in here like that? So these two ratios are the same, equal to the same ratio. That's why they are actually the compression rates, because the same ratio of the volumes. And So it's the same quantity. Hence, that proves that expression. Pause. Okay, so we found the expression that we're supposed to find, that the ratio, these two ratios are the same because they're equal to the same number, V2 over V1. Basically the compression rates, or however you want to define them. So the point being in here is that we found that ratio to be the same, and then the question B, determine the work in terms of the CR during the expansion phase and during the compression. The quantity that I defined earlier as being CR is actually called rho. Okay, so hopefully you guys would have made that distinction between it. Anyway, so let's find the expansion phase, the work during the expansion phase. Remember, the expansion phase is really in this isothermal. So we need to find W in here. There is no work in here. W is equal to 0 here. So this W is going to be negative. This W is going to be 0 in here again because it's an isochoric process. This W at the end in here because we're going, so this is the direction with which we're going clockwise. So the net W is going to be negative, and here it's going to be actually positive, but this is happening at TC, which is less than TH, so this work is going to be less than that work, an absolute value. So the net work is going to be positive. So let's find W hot first of all, the first cycle. Okay, for part B. So the question to part B. That W, we did a calculation already. It's equal to minus NR TH ln of the ratio of the final volume over the initial volume, V2 over V1. It's the same volume. And that ratio is PC over PB, which is CR, okay? We just can use that expression, minus NRTH ln of CR. Okay, good. So we have that. And then we also were supposed to find, so this is the first W. The second question was to find the work, or the question C is to find the work for the cycle that involves the TC. So this is the demonstration. This is the solution for the problem that I demoed earlier with the Stirling engines. Actually, we had two of them. So the final volume is actually V1. The initial volume is V2. And again, this ratio, we can flip it, and it's going to be a positive, minus NR TC ln of CR, because V2 over V1 is actually CR. Obviously, like I said, because TH is higher than TC, those two numbers are the same, with the exception the difference in temperature is actually the net work in here. So I think it's the next question, is it? An ideal engine. So now question D was basically, so they didn't ask for the W net, but it's quickly very easy. The net work in this case is going to be a negative number, so it's going to be minus NR ln of CR times the difference in temperature between TH and TC. Okay, so if you want to find the efficiency of this engine, you really have to find the Q's also. Okay, so there is a Q in here which is equal to the positive of that one, but there is actually a Q in here too, which is equal to so during AD, dA, we're going from a higher temperature to a lower temperature, so the Q is going to be positive actually, so there is heat injected into the system in this case, so it's going to be, I'm sorry, it's going to be negative because we're getting rid of the heat in this case, because T final is TC and T initial is TH. So it's going to be N times CV times the difference in the temperature, which is TC minus TH. Okay. So this is basically how much heat there is in this case, and then the heat in this case is going to be N times CV times the final temperature TH minus TC. So this is heat injected in the system. So this is the additional heat that we're going to gain from the process. So this is part of QH. So this is part of QH, not all of QH, because there is another QH in here too. So both of them, they will add up to the QH. So it's this value, add to it that value. And now if I want to find the efficiency of this engine, what I'm going to say is that W that we just calculated, the net W, in absolute value because it's going to be negative, okay, divided by this two heats in here, so it's going to be divided by NCV times T final minus T initial, plus the other heat, which is equal to nRT H times ln of CR, times the ratio of these two volumes, which is CR. Okay, so that's basically how the efficiency of this engine looks like. Okay, but they didn't ask us these questions. They jumped right away into an ideal Stirling engine uses 1 mole, so they gave us specific numbers in here. So we have N equals to 1. Mole. What else did they give us? Okay. Of helium. Helium is a diatomic, is a monoatomic gas, so we know CV for helium is 3/2. Okay, it's very important. We need that. Okay, if we are going to ever find efficiencies and stuff like that. And they told us that it's working and has a CR equals to 10. So the ratio of the volumes is 10. Okay. And then temperature reservoirs, so we know TH is 100 degrees Celsius. Don't forget to convert this stuff to Kelvin, except when you're dealing with difference, because TH minus TC, whether it's in Kelvin or in 20 degrees Celsius, whether in Kelvin or degrees Celsius is the same difference. So if we're dealing with difference like in here, doesn't matter, you don't need to do conversions. If we're dealing with this one, we don't need to worry about it. This one we don't need to worry about it. This one actually we don't. So actually there is no need to convert anything, so just leave it in TCs in this case. Okay, if we're going to calculate entropies, yes we do. Okay, what is its power? Oh, and they said it's a frequency of 100 hertz. That means in 1 second this does 100 cycles. Okay, 100 times goes up and down. Remember the engine in the demo? Okay, so that's how often. So this is a very fast engine. Okay, so that's your RPM of the car, basically. What is the rotations per minute? Okay, they want to find the power. Remember the power, I'm going to use this one in here so that they don't confuse it with the pressure, is equal to the work divided by the time it takes to do this whole thing. Okay, the work for 1 cycle over the time that 1 cycle takes. So 1 second it's 100 cycles, so 1 cycle takes 100th of that amount. Okay, so very straightforward in here in this case. Or if you wish, you need to find the work of 1 cycle. The work of 1 cycle is given by this expression, minus nr ln of CR times the difference in temperature, and n is given, r is given. So we don't need CV at all. It's just the power that concerns us. Okay, do we? No, we don't. Do we need it in here? Oh, and yeah, there is no work in here, so the net work, so we're done. So we are done. We have W, N is 1, R is 8.314, ln of 10 times 80 minus 100 minus 20, which is 80, and that's your network. And you divide it by a time to do 1 cycle, because that's in 1 cycle. Okay, or multiply it by 100 to find it in 1 second, because the power also is the work done in 1 second. So all you have to do is multiply it by the frequency, which is the number of cycles per second, and that's it. So that's basically what the expression is going to be at the end. It's going to be 100. That's how many cycles in 1 second. That's how many work in 1 second, basically. So this is basically per second, because remember the frequency in here is equal to 100 hertz. That's given to us. Times the work. The work is equal to, I'm going to take it in absolute value again, because we don't care for the, what is the power output. Yeah, so that's easy. N is 1, the number of moles is 1, times 8.314 times ln of 10 times 100 minus 20, that's 80. Okay, and we have the answer. So whatever that number is going to be is going to be. Let's see here. Okay, so it's going to be in watts, okay? Because everything is in SI in here, so everything should be in watts in here. Okay. Please finish this one. That's another question of the day. Calculation. Furthermore, now you should be able to find the efficiency of this engine, E. Okay, you have the formula for it. I just wrote it in red, I believe. So you have the W net. You know what CV is for a monoatomic gas because it's helium. It's 3/2. Your number of moles is 1. The difference in temperature is 80. Okay, so you have the expression in here. 3/2 of an R. I'm sorry, did I say 3/2? CV is 3/2 of an R. Don't forget the R in here. Okay, that's what CV is for a monoatomic gas. And then you have NR times TH, which is, now you have to convert. TH is in Kelvin, not in, don't put 100 in here, it's 373 times ln of 10, and you're done. You should find how efficient is it. It's an interesting question also, so if you have something like this in an exam, to compare it to, so you're going to find a number in here, okay? I don't know what it is, but you're going to find it. You're going to compare it to the efficiency in here due to an engine that is running if it's a Carnot cycle, and the Carnot cycle in this case is operating between 100 degrees Celsius and 20 degrees Celsius, so it's 293 over 373. All I did is add 100 to 273 and I add 20 to 273, and that is the efficiency of the engine. So let me do the math again quickly here. Didn't we do this earlier? I think I did. Let me quickly do it again. It's 1 minus 293 over, what is it, 373. So the efficiency is 21%. I remember we did that, okay? So the efficiency is what in another context, but that's really what it is. You should not find an efficiency more than this number. So this number I know must be less than 21%. If you find it more, please let me know. That is another question of the day, and that is to verify the statement in here. Find the efficiency. I know it's not part of the question for this problem, but again, if you're tested in these points, you're going to be expected to know how to find the efficiency of an engine, and you can actually do that too and find the how efficient this engine is. Okay. Furthermore, we should be able to find the entropy, the change in entropy overall for this cycle. We have Q over, and here the entire Q is going to be independent of temperature. Temperature is constant, so it's going to be just NR ln of CR, okay? And in here, so it's going to be a positive number in here, so the entropy is going up actually in here. So delta S for this portion is going to be the ratio of heat over TH, so that's going to be a positive NR ln of CR. Okay, same thing in here is actually going to be a negative number, and it's going to be the same thing, minus NR ln of CR. Here is where you need to do some calculations. Okay, you have dq actually, which is equal to NC v dt. So you have to find the ratios and involve the ln's and do the calculation for that and calculation for the other one, and see how much overall entropy for the system. So again, if this question is part of an exam, you're supposed to know how to also calculate delta S for any simple process or for the overall process. The reason why I took Q over TH in this case is because I know that the temperature is constant. So when I integrate, the T comes out, so it's just going to be the total Q. So dq over T in an isothermal process. So this will come out of the integral because T is constant in an isothermal process. So it's just going to be Q over T. So in this case, T is TH, and I had TH in here, cancel the TH in there. So that's why I wrote it this way. But in this process in here, the temperature is not constant. As a matter of fact, it changes from TH to TC. and dq in this case is equal to ncv dt, and now they're going to involve a log when I divide by t and integrate from t initial to t final. So you have to be careful with this stuff. So I'm hoping that you guys can follow the examples in the book and do the examples in the book and finish this one. And if you have any questions, please let me know. These two recordings are very long. I still have, as I promised, a few more problems to discuss in this chapter, 34, 42, 52, and 53, and those are part of your exam preparation too. So all of this stuff that I did so far for this chapter and the chapter before and the chapter before are preparing you for the exam that is coming soon now. Please take care of the questions of the day and make sure you answer them part of the discussion. And let me know about this thing in here. If the efficiency turned out to be more than 21%, it should not be. If it is, then we have to do it together. Thank you.